Hi, my name is Cole Porter, and I'll be doing a video presentation on the 4 fundamental forces of nature. The 4 fundamental forces of nature are the forces that govern basically how the universe works and how matter and how things interact with each other. And these 4 forces are gravity, electromagnetism, the strong nuclear force, the strong interaction, and the weak nuclear force or weak interaction. And as I said, these forces basically govern everything that happens around us, from how planets orbit around the sun, how magnets work, electricity, the structure of nuclei, and also some forms of radiation. And we're going to start off talking about gravity. Now, gravity is a force, and it describes basically interactions between two objects of mass. The force of gravity is a function of mass and distance. And the greater the mass, the greater the force, and the greater the distance, the weaker the force. And these two variables are brought together by the gravitational constant. And if we put these 3 things, mass, distance, and gravitational constant, together, we can find that the force equals the gravitational constant times the mass of object 1 times the mass of object 2 over the distance between them squared. And now this can be used to determine the force of gravity between any 2 objects. And most often we use it for describing the force of gravity that the Earth exerts on objects, on us. And we can find that the gravitational acceleration of the Earth equals the gravitational constant times the mass of the Earth divided by the radius of the Earth. And if we plug all those numbers in, the mass of the Earth, the radius of the Earth, and the gravitational constant, we find that the gravitational acceleration that the Earth causes on objects equals 9.8 meters per second squared. And with this acceleration, we can plug that into kinematic formulas, and we can find the potential energy of a falling object, the force of a falling object. We can find the velocity and distance traveled of a falling object. And together, these things, these equations, this theory of gravity helps us to understand how planes work, how rockets and space exploration work, understanding planetary and solar orbits, and any other thing that involves jumping or running or throwing, anything that involves falling and gravity. We can use these theories and these equations to help us understand them a little bit better. And that is gravity. The next force we're talking about is electromagnetism, and this theory ties together both electricity and magnetism. And it describes interactions between charges, and that like charges, both positive and negative, like charges repel each other and opposites attract. It also describes that moving charges within a system causes magnetic fields, and that magnetic fields can interact with charges, and all these things interact together, and there's tons of equations that describe how the force between 2 charges is, and how magnetic fields can impact velocity and angles and all that stuff. We won't get into that. But although electricity and magnetism are different, they are one unified force. They describe the same thing. They describe interactions between charged particles. And these interactions are very important. They describe interaction between electrons and protons. They describe chemical bonds, chemical interactions, and chemical reactions. They govern human physiology, animal physiology, plant physiology, brain waves, electrical impulses, hormones. Everything that happens within our body is a product of electromagnetism and those interactions between things. And most importantly, magnets. So that is a brief overview of electromagnetism. The next force is the strong nuclear force or the strong interaction. This force governs basically the structure of nuclei. Normally, protons as charged particles would repel each other, as electromagnetism would describe. But the strong nuclear force actually causes protons to attract to each other and hold together within a nucleus. And that's because that the strong nuclear force is very strong. It's actually 10 to the 38 times greater than the force of gravity. And although it's a lot more powerful than gravity, it's only effective at small distances. So basically, these protons have to be very, very close together for this force to have any sort of impact. Which is why that the bigger the nucleus is, the weaker the strong nuclear force is, the weaker the strong interaction is between protons. Which is why that extremely large nuclei are unstable and are prone to decay. Which brings us to our next interaction, which is the weak nuclear force. And the weak nuclear force, the weak interaction, governs decay of nuclei, meaning that a neutron, through the weak interaction, through the weak force, can become a positively charged proton, a negatively charged electron, and an antineutron. An antineutron is a subatomic particle that I won't get into, but it is a product of what's called beta decay. And beta decay is a type of radiation. And it happens, for example, this equation, you have thorium, which has 90 protons and 234 protons and neutrons. And if it goes through beta decay, if this weak nuclear force interacts with a neutron, it ejects an electron and it gains a proton, thus turning into protactinium, and thus changing it into a completely new element. And this interaction is, because it's subatomic as well, it's not effective at great distances, which is why it only happens within nuclei. It's the cause of some forms of radiation. It uses the decay of mesons, which are particles that help with the strong nuclear force, which is why you see some forms of decay. And it also is important in the nuclear fusion of the sun. So all these forces, again, like I said, work together and determine basically everything we see around us and all these interactions. And I hope this presentation was informative and helpful. Thank you so much.